All right, good morning. Let's begin. The next homework assignment is there on the screen. Of course, if you ever want to know what it is before you see it on the announcements, you can just look at the course schedule because the assignments are listed there. After class, you can, if you didn't already, pick up the quiz that's been graded, and most of the last homework assignments are there. There's still a few papers that are being reviewed. So we're going to start talking about hydrostatic forces today, and this is a really interesting and important topic, so I'm glad that we have a chance to dive into it. There are several examples I want to work through with you today to help you understand this concept. Before we get started talking about hydrostatic forces, are there any questions related to the announcements? All right. Oh, by the way, with the quizzes or homework, anytime you have questions, like if you think there's been a mistake in grading, or if you don't understand the points deduction from a quiz, I'm happy to go over that with you. Please stop by during my office hours and we can definitely sit down and have a chat. All right. One thing I wanted to start off with to remind you of the idea is area moment of inertia. And this is a topic that I think you probably covered when you were in your statics class. And area moment of inertia we label with the variable I. And there's a table of these values in the back of your book. It looks a little bit different from this figure, but I'm just showing this figure because it sort of shows up fairly clear on the screen. What you need to know is that depending on the shape, the area moment of inertia changes. And what we'll see most often is rectangle in hydrostatic forces, because the rectangular shape happens to be the shape that a gate that's holding back maybe water in a tank would be. Sometimes we'll see, and so the area moment of inertia formula for a rectangle is AB cubed divided by 12, where A is the horizontal component and B is the vertically oriented component. Yeah, so we're cubing the component that's vertically oriented. In the case of a circle, area moment of inertia you can see is pi r to the fourth divided by 4. And so there's other shapes there that we may come back to, but you can find those formulas and the dimension definitions in the back of your book. Okay, so with that concept just reminded to you, let's talk about the type of problems you can expect to see here in this chapter. Try to visualize what we're looking at here is the side view of a gate holding back water. We've got a hinge, so you can see that the gate would rotate outward because of the hydrostatic forces pushing on that gate. We're going to have to somehow resist it, otherwise the gate's going to rotate at the hinge and water is going to begin spilling out. So the type of questions we would maybe see in this chapter is how hard is the water pushing on the gate? And what you already know is that pressure increases as you go down through a fluid. And so the longer this gate is, the higher the pressure will be at the bottom of the gate. And this is how we would apply the area moment of inertia definition to this gate. Now, you'll notice that they gave you some dimension above the hinge. But in this case, B isn't the physical height of the gate. B is just the vertical dimension from the water line down to the edge of the gate. So that's an important distinction you need to keep in mind, is that we really only care what's happening below the surface when we're calculating the hydrostatic forces, because above the liquid surface it's just a gas that's really not pressing very hard, relatively speaking, onto the gate. So the hydrostatic forces here just depend on the 4 meters associated with B. And so if the area moment of inertia is AB cubed divided by 12, we would use 3 meters as the A, 4 meters as the B that is then cubed. So that's what we're going to do. We'll circle back to this exact question, and I'll show you how hard the water is pushing on the gate. And what it'll depend on is the increase in pressure. And so you can see that there's a linear increase in pressure. There's a triangular pressure distribution here where there's 0 pressure at the top and the pressure at the bottom is the highest. Does anybody remember what the slope of this line is? It's the unit weight. Because if we go back to the hydrostatic equation, delta P is delta H times gamma, where gamma is the unit weight. And so This gamma, the unit weight of water, is the rate of pressure increase. And so as we go down through water, the pressure is increasing at 9810 pascals for every meter of depth that we go into the fluid. And so that is why this is triangular, because it's a linear increase in pressure. What's the formula for force where we've got some area and some pressure? What do we do to those two variables to calculate force? Force is what? Pressure times area, right. And the way that we remind ourselves of that is, let's take a look at the units. Pressure is units of, in terms of newtons per meter squared, which is the same as a Pascal. And if we multiply that by area, which is meters squared, then we will get newtons. So if you're ever not exactly sure how the variables fit together, you can sometimes figure it out by examining the units, and that will remind you of the formula. All right, so hydrostatic force here, we're going to consider the area of the gate and then the pressure. You can see that the pressure is changing. And so we'll go through the procedure of how do you come up with like sort of the average pressure that you should use to find the hydrostatic force. Ultimately, what we'll do, you can see now I've put in this brown big thick line here. What this represents is the equivalent hydrostatic force. There's not just one force acting on the gate. Everywhere the pressure is pushing on the gate, there's a little bit of force. But what we want to do is find out, considering all of the pressure over the entire gate, if we accumulate it and we said, let's say, where is one equivalent force located and how big is it? That's the sort of thing we're trying to figure out, is the equivalent hydrostatic force due to pressure acting over an area. Any questions about that big idea? Because this is an important one. All right, so let's hit some terminology just to begin. We're going to consider a plate that is submerged in water. And here you can see this plate happens to be inclined. Sometimes we'll do surfaces that are vertically oriented, and that'll make the problems a little bit easier when they're vertically oriented. Sometimes they'll be inclined. Sometimes they'll even be horizontal, and that makes it easy too. But let's apply these definitions for a inclined plate like this. Delta H is the distance from the water surface down to the centroid of the object. And so the centroid is the center of area. So let me just draw a little dot here in the center of this object. So you can see from the side view, you can see the height of it. And from the front view, if we looked at this object this way, if we're looking at the plate from this direction, what we would then be able to see is how wide it is. But we wouldn't say that this is A. Why is that? Why is it that we wouldn't say that this distance is A? Because it's inclined, and it may look shorter than it actually is. So this is an inclined height. So what tells us the actual length of this plate is when we're looking at it from the side. And so we get the width of it this way, B from one view and A from another. Okay, so here's the centroid. The centroid is the center of area. And so if I draw the centroid here, it's just sort of in the middle of the two edges of the plate. And now I'm going to go up to the water surface, to the edge. Let's say that this tank is completely full. So that's delta H. It's the distance from the centroid to the water surface. And it's a vertical distance. You're not taking some strange route. You're not going in circles up to the surface. It's the most direct vertical distance from the centroid up to the water height. Okay, P, or sometimes we call it P bar, is the pressure at the centroid. So how do we find out what is the pressure at this location? We just apply the hydrostatic equation. It's going to be delta H times gamma. So we'll use the vertical distance from the centroid to the water surface and multiply it by gamma, and then that tells us what is the water pressure at the centroid. Now y bar is the inclined distance. We're still going from the centroid and we're still going to the water surface, but instead of going straight up, we're going along the same inclined path as the plate. So let me draw, here is y bar, the inclined distance from the water surface to the centroid. So does everyone understand the difference between y bar and delta H? Okay. YCP is the distance from the water surface to the center of pressure. Centroid is the center of area. Center of pressure is different. Let me bring back the previous slide we were just looking at and see if we can figure out where the center of pressure is. I've already maybe given you a hint, but here's the pressure, right? We want to find out where is it that where is it that half of the area of this triangle is above it and half of the area of this triangle is below it? 1/3, right. It's 1/3 from the bottom, so 2/3 from the top. So that is the center of area for the pressure distribution, right? So if we go back to this next one, YCP is what we're going to call the distance, the inclined distance from here down to where this equivalent hydrostatic force is. So I'm going to draw, we're going to have a little bit of an offset here. Okay, so YCP is going to be the inclined distance from the water surface to where the force is located. So we have a formula that tells us YCP. And sometimes we use that formula to find the overall distance from the water to the location of the force. And sometimes we rearrange it just slightly to tell us how far is YCP located below y bar. So sometimes what I'm saying is we just want to know that distance. Depending on how we rearrange the formula, it can tell us either. So far, I just want you to know the definitions. There's basically 1, 2, 3, 4. If you can remember these 4 definitions, then most of the problem solving should come fairly easily to you. Remember, YCP, I've done these offsets here, but it is still just the water surface to the location of the force. If I brought this dimension back, it's going to be from the water surface to where the F is located. Any questions? Yes? Uh-huh. It's the same angle that the plate is located. And so what I'd usually give you, or what you'll see in problem statements, is they'll tell you maybe from here to there, 45 degrees. And so you'll be given some sort of indication of how this plate is oriented in the water. Good question. I'm glad you asked that. All right. Here's the formula. This is how we can calculate YCP. Now y bar, remember, is the distance from the centroid to the water surface along the inclined route. So we can just figure that out by inspection, just by looking at the drawing, or sometimes we'll have to do some small geometry. And actually, this is going to be strange because maybe the last time you did geometry was back in middle school, right? It's been a while. So you're going to remember 3, 4, 5 triangles and sine of 45 degrees, all that sort of old stuff. So you'll find y bar by some geometry or inspection. I is the area moment of inertia that depends on the shape of the figure that we're having the force acting on. Area also has to do with the shape of if it's a gate or some sort of a metal plate submerged down in water. So it's a relatively straightforward formula, and that will tell us how far it is along the slant of that inclined plate from the water surface to the center of pressure. And center of pressure is where the force is located. So just to remind you, center of pressure means that's where the equivalent hydrostatic force is placed. So here we are, circling back to this problem. What is the magnitude of the force and what is the location? So what I'm going to show you is I'll bring up the solution to this one, and then I have a similar one that I'd like you to do the calculations yourself for. All right, so let me bring up the solution and I'll show you how we do this. Okay, so the steps, that if we break it down into the smallest chunks, we first of all want to examine the geometry of the plate. So you can see here, A, the width of the plate is 3 meters, and B is 4 meters. So we go back here, 3 meters is the side view, 4 meters we can see from the front view. So that's the shape that we need to use. First thing we do, step 1, find the distance to the centroid, delta H. So the centroid of the rectangle is going to be in the middle of it. So we can see from the water surface down to the middle is 2 meters. So you can see here I'm saying it's B divided by 2, so delta H is 2 meters. Step 2, find the pressure at the centroid. So we're going to apply the hydrostatic equation, delta H times gamma, and that's going to tell us what is the water pressure at the center of the plate. And you can see I've done the calculations there, and I'm using the unit weight 9790 because on the problem slide it said 20 degrees Celsius water. So water at 20 Celsius has a unit weight of 9790. So we multiply the depth to the centroid and the unit weight. That gives us this 19,580 newtons per meter squared. Okay, step 3 is find the hydrostatic force. Pressure times area. And so that's the magnitude. Of the two things that this problem is asking, we found the first one really easily. Just the force, the magnitude of the force is the pressure at the centroid multiplied by the area of the plate. So any questions so far on how we went through these first 3 steps to find the magnitude of the hydrostatic force? That's how hard the water is pushing on this gate. Now where the water is pushing on this gate, the location of the equivalent hydrostatic force is really important because this is ultimately going to turn into a moment analysis. We've got the hydrostatic force pushing on the gate on one location, and then we're trying to keep the gate closed by pushing here at the bottom of it with a certain force. So how deep into the water that hydrostatic force is pushing is pretty important for us to be able to solve the moment analysis at the end. Okay, so the location of hydrostatic force. We have to know y bar. And remember, the definition of y bar is the inclined distance from the centroid to the surface. But since this is a vertically oriented pipe, a plate, it's the same distance. Vertically oriented is the same as the slant distance, and so y bar and delta H are both 2 meters. So that's going to make our formula for YCP pretty simple. I've calculated the area moment of inertia here because I know I'm going to need it. I wish I could turn this thing off. It really is irritating. It fades away eventually. But all right, so here's the area moment of inertia, AB cubed divided by 12. I calculate that because I know I'm going to need it in the last part of the problem where I'm calculating the inclined distance to the center of pressure. So y bar plus I divided by y bar A. So y bar is 2 meters. Here's our area moment of inertia. 2 meters times the area of 12. So 2.667. And earlier when we were talking about it, most people already knew it was 2/3 of the depth into the water, right? So what's 2/3 of 4? It's that, 2.667, right. So now we know the magnitude of the hydrostatic force, the location of the hydrostatic force, and if we want to know how big is F that's resisting that hydrostatic force, the last thing we do is a moment analysis. And so here I'm saying, here's the hydrostatic force acting at 2.667 meters down from the edge of the hinge, because the hinge is at the water surface. And here is our unknown gate closing force of F. That's 4 meters vertically from the hinge. And so if we do the moment analysis now, it's 156,640 newtons. So it's just a step-by-step procedure. And if you follow these same steps in your own calculations, then it'll work out fine. Now, it gets more complicated when it's an inclined plate, but it's not unsolvable by any means. Any questions before we move on? Yeah. Okay, good question. So if the water level was above the hinge, then what that would mean is that some of the water is... Exactly. So here's the hinge. You've got some of the pressure here, some of it's there. So you'd need to calculate, you'd need to break it up into two different pieces. You need to find out on this piece what's the magnitude and the force and the location, and then on this piece, what's the magnitude and the location. All right. Here's the one I'd like you to get started with. Okay, we have a gate. There's a hinge. So we want to know, in this case, we're not going to do the moment analysis at the end. All it's asking is find the magnitude and location of a hydrostatic force acting on the gate. This one's a little bit different because the hinge is not at the water surface. It's below the water surface. Here, H is 6 meters, and the gate is 3 meters tall, and then 2 meters into the page. The width parameter is 2 meters. It's the same 20 degrees Celsius water, so you'll use a unit weight of 9790. But here's the formulas. You can go through the same steps that were outlined on the previous example, but let me bring up the lights and you can start working with your classmates on this one to find the magnitude and location of the hydrostatic force. Force on a... All right, so this is a tricky problem. It's loaded with surprises. The first one is, of course, the distance from the hinge to the centroid is 1.5 meters, but the depth to the centroid has to go all the way up to the water surface. And so you add that 1.5 to the 3 meters that is above the hinge to the water surface. And so that's why we're saying delta H is 4.5. Okay, so now if some of you only saw the 1.5, now you won't make the same mistake ever again because you'll remember that it's all the way up to the water surface. Okay, step 2, what's the pressure at the centroid? So 44 kilopascals is at the centroid. Magnitude of the hydrostatic force is the pressure at the centroid. So this P with a line over it, I sometimes will call that P bar. That just means pressure at the centroid. It's a pressure at a specific point. Pressure at the centroid times the area. So the magnitude of the hydrostatic force is 264 kilonewtons. All right. Any questions so far? All right. Then the location of the force. Vertically oriented plates are nice because y bar and delta H are the same distance. So you calculate the area moment of inertia and then the YCP. So that's where the force is located. And a warning, an answer is not completely right unless you've also included the units. So when I'm being at my most picky, like when I'm grading an exam, if you didn't write the units, I'd take off a little point, maybe half a point. But because especially when I'm asking, what is some distance in millimeters, then I want to be certain that you've made the conversion that's intended. So, hydrostatic forces. Any questions about the example? All right. Let's look at some more, because the best way for us to see all the curveballs we can get is through more curveballs. So here's an inclined one. We're going to take a look at what happens when a 2x3 plate is, the top edge of the plate is 5 meters from the surface, and it's inclined at a 45-degree angle. Now, because I want us to be able to get through several of these, I'm just going to pull up the solution and I'll show you how you handle the angle, and then we have another one at an angle that I'll have you do the calculations on with some free time. Okay, so it's going to be the same basic procedures. You can see that I've labeled them here. First, we're going to find the depth of the centroid. Then we'll find the magnitude of the force, area moment of inertia, location of the force. Okay, so by inspection, that means just by looking at it, by inspection. Where is the centroid here? It's at the center, right? So here is the centroid. So the depth of the centroid is going to be the 5 meters. Let's see, 5 meters and then some more. So this up to the water surface is 5 meters. And then some more depth too. So we're going to have to add that to get our overall delta H. Okay, so part of the geometry is going to kick in when we know that this is 1.5, the slanted distance of it, but it's not the slanted distance that we're going to add to the 5. All right, so let's take a look at how we handle that one. Oops, all right. All right, so I've got a really poor drawing here, but it's a drawing nonetheless. So our depth of the centroid is the 5 meters, which is the vertical distance that's given, plus 1.5 times the sine of 45 degrees. So that tells me the vertical component of that 1.5 meters. And so the sine of 45 is 0.7071. So if we add those two pieces together, then it's 6.061 meters. And that's the vertical distance from the water surface down to the centroid. Yeah? No, so we're not doing the inclined distance. Let me draw this again right here. Okay. So here's the plate. Here's the centroid, and we know that this is 5 meters. Okay, we want to know how far is it here. This is delta H. Delta H. And what I'm saying here is that delta H is 5, and then this distance is going to be 1.5 times the sine of 45 degrees. And so it's going to be less than 1.5 meters, because if it was like this, then we'd add the 1.5 meters. But as we turn it, then less of that 1.5 meters is in the vertical direction. And so when we do the sine of 45 by 1.5, then that's 1.061 meters is the vertical component of that inclined plate. So depth of the centroid is still just straight to the surface, even though we have to find out, here's the inclined plate, but how much of that inclined plate is in the vertical direction? So this sine of 45 tells us the vertical component of the 1.5 meters. A little tricky, but we've got the depth of the centroid. So the magnitude of the force is the same thing, just P bar times A. The way that we find the P bar, of course, is the delta H times the unit weight. So here are the three things: the depth of the centroid, the unit weight of the water, and the area of the plate. Those three things gives us the magnitude of the force. Magnitude of the force that's acting on the front side of this plate, F. Okay? So many examples. All right. That's the wrong one? Ah, geez, I need to close some of these. That's the one. All right, so then the area moment of inertia, AB cubed divided by 12, because I'm going to need it when I find the location of the force. Okay, now here's where the geometry kicks in again. I know that the depth of the centroid is 6.061 meters. So that's the vertical component of this triangle. Now, the inclined distance from the centroid to the water surface, that's what we call y bar. So if I want to know y bar, it's going to be 6.061, which is this edge of the triangle, divided by the sine of 45. And that will give me the distance along the inclined route to the water surface from the centroid. So 8.572 meters is the inclined distance to the centroid. But what I really want to know is the inclined distance to the center of pressure. Why? What's special about the center of pressure? That's where the force is located, right? So we know the magnitude of the force already, but we want to know where is the force actually pushing on the gate. And it pushes on the gate at the center of pressure. It doesn't push on the gate at the centroid. It pushes below the centroid. The center of pressure is always below the centroid, sometimes by a little, sometimes by a lot. the deeper into the water this plate is, the closer those two distances get together. So here I'm going to use the formula for YCP. It's just y bar plus I divided by y bar A. And you can see that done the calculations there, and there finally I have the inclined distance to the center of pressure. So this YCP that I've calculated, what that tells me, let me show you here on the board. That tells me we always knew that there was going to be some force pushing on the plate. We found the magnitude of it. The YCP tells me how far it is up to the water surface. From the water surface, inclined distance down to the location of that force. All right. That's the procedure. Here are the numbers on the screen. But I'd like you to get a chance at trying to calculate for an inclined plate. So let's look at this one. The magnitude of the force we found earlier. Yeah. The magnitude of the force we found, yeah, it was up here, 356 kilonewtons. All right. So here is a tank of water with a circular pipe coming in. If you cut a circular pipe at an angle, what you end up with is the shape of an ellipse. So think about a circular pipe. I'm going to roll up a piece of paper into a circular cross-section. And now think about cutting that at an angle. And so what sort of a shape would you need to be a cover for that circular pipe cut at an angle? The shape of it would look like this, if that was going to be a plate that's covering it so that no water leaks through that cut pipe. So that's what this illustration is showing. It's saying we've got 5 meters is the dimension from the top to the bottom of the ellipse. And so here, the area moment of inertia formula goes from the centroid up to the edge for B. So this distance of 5 meters, that's actually 2B, as shown on there. The 4 meter diameter, that's going to tell us the width of the ellipse, because here A is from the center to the edge, and so 4 meters is the width. 2A gives us 4 meters. And if you've got a triangle that is 5 meters on one edge and 4 meters on the other, then what do we know about the remaining? 3, right. So this is a 3, 4, 5 triangle. That's going to be useful when you go through the procedure of, first of all, find the magnitude of the hydrostatic force. Now remember, we do that by finding what is the delta H, what is P bar, and then the magnitude of the force is P bar times the area. Okay? The inclined distance to the center of pressure, well, first of all, we need to know the inclined distance to the centroid. And then once you know the inclined distance to the centroid, then you use YCP is y bar plus I divided by y bar A. That's the formula for YCP. And then the last step here, the force required to open the gate. We're going to do a small moment analysis where we have the force is acting. If here is the centroid, the force will be a little bit below the centroid. So here's the hydrostatic force pushing the gate closed. And what if we want to open the gate? How much are we going to have to pull on that? All right. Same procedure as before, it's at a different angle. Okay, so let me pause the recording, bring up the lights, and give you... I wish this class was 75 minutes long, but it's not. It's only 50 minutes long. You probably are glad that it's 50 minutes long, but anyways. All right, let's look at the solution for this one just so you can see if you were headed in the right track. As I was walking around, I saw many of you are already getting the geometry figured out just fine. So here we go, pipe gate. Okay, so A is 2, B is 2.5. And there we can find the area just as a starting off thing. It's 15.708 square meters. Okay, the depth of the centroid is 10 meters. Because the vertical component here you get from the diameter of the pipe. So it's 8 meters to the edge and then another 2 meters down to the centroid. The magnitude of the force is the pressure at the centroid times the area. So that's the same as delta H times the unit weight. That gives you the pressure at the centroid multiplied by the area. So 1.54 meganewtons. That's the magnitude of the force. All right, now the inclined distance to the center of the pressure, I solved that one by comparing like triangles. If we've got a 3, 4, 5 triangle, that happens to be the same shape and the same angles as the vertical component is 10 meters. That's the depth to the centroid vertically. And y bar is the inclined distance from the centroid to the water surface. So I just compare these two triangles together, and then I get that y bar is 12.5 meters. Now there's other ways to do it. If you want to find this angle here and then do like sine and cosines, then you can find y bar in another way. But this is just, for me, it was the most straightforward approach. So I have the y bar. I've got the area moment of inertia. I can now find the YCP. Now, if this is a moment analysis, I was thinking it's more useful if you are doing the moment analysis to know the distance from the centroid to where the force is located. So this 0.125, that is the distance between, here is the centroid of the gate, and then the force is a little bit lower. So I wanted to know that gap distance there is 0.125, because then I can add that to the distance from the edge of the pipe down to the centroid. So anyways, if we do the full force balance, then the drawing in the lower left shows you it's 5 meters is the full distance of the gate, and so we're opening at the edge of it with this unknown force, and the 1.54 is acting to close the gate, and it's 2.625 meters from the hinge to where the force is located. So then the force would be 0.809 meganewtons. Okay, in the 1 minute remaining, I just want to show you what happens if the pipe is actually flat, laying flat like this. To find the force, you find the pressure and multiply it by the area. So the pressure is going to be 5 meters of depth times 9810 gives you the pressure, and then the area of this plate is 6 square meters. So that's how you'd find the force. But here's the important fact. The weight of the water is the same as the force acting at that depth. So let me show you. Doesn't matter how you, let's see, horizontal plate. It doesn't matter if you calculate it from the pressure at the centroid approach or the weight of the water, but you get the same force. 294 newtons would be the pressure acting over 6 square meters, or you just find out how much water is actually above that plate and what is the weight of it. It's the same thing. And we'll come back to this idea of the weight of the water above the plate when we talk about curved gates next time. So that's all that we've got for today. If you didn't already pick up your quiz or the homework, then you can get that at the front table. See you on Tuesday. Yes. Yes.